Another one in line with which works in the combined electric and magnetic field is called a cyclotron, right? Now this is the diagram or a rough sketch of how it looks like. Okay, so you have these electromagnets or permanent magnets. Permanent magnets will become very heavy normally. So we use an electromagnet. The purpose at the end of the day is to create a magnetic field, right? And the magnetic field directed will be directed from North Pole from the North Pole to the South Pole, right? So they are directed something like that. Okay, they are directed like that. And these are the copper D's. Okay, these are the copper D's. This copper colored thing, this is a copper D. Okay, a semicircular copper D. And same with this, and same with this. They are a semicircular hollow copper D's, right? We'll soon see why we require them. So we have in effect a magnetic field that is into the into this, right, coming from the top and piercing the whole thing and going down. And then these copper D's are connected across the copper D's. You have a high frequency alternating voltage connected, right? So that is normally achieved by an oscillator. This is achieved by an oscillator. Right? An oscillator actually kind of oscillates the voltage polarity between them. So what happens? It is kind of plus here and a minus here and a minus here. After some time, you'll find that the minus has become plus and this has become minus. After some time again, this becomes plus and this becomes minus. So it keeps on flipping the voltage between the two, right? Now why and why it does that and what happens due to that, we will soon see. So it is a thing where if this is at a positive and this is negative, then there is an electric field between the D's in this direction, right? In this direction, like that, right? And when it is negative, it turns back in the opposite direction. So it is something like that. You can see that black thing, black line, and the arrow is like that. You see? So this is the electric field. Electric field is in the plane of the copper D, and perpendicular to that you have the magnetic field, right? The magnetic field is perpendicular to that. Now what happens due to that, we'll see once you understand the diagram here. The schematic diagram is shown here. Okay, so this is the simplified version of it. Here you will understand things better. So we have shown it from the top, right? So this is being shown from the top. So the field lines were originating here and entering here. So we have shown it in by a cross. So looking from up, this is a cross, and this is the oscillator we were talking about. This is what is named in the above diagram as high frequency alternating voltage. That is what the oscillator is, right? And then we put a charged particle inside, correct? So let us first talk about the construction of the construction of the cyclotron. So the construction part is that we have two hollow copper Ds with magnetic field perpendicular to them, perpendicular to them, right? And then we have an oscillator. we have an oscillator with a fixed frequency, with a fixed frequency to change the polarity, to change the polarity of the voltage across the D, to change the polarity of the voltage across the D, right? Somewhere here in the center, we place a charged particle. Okay, so and here we have a way of deflecting the whole thing because it keeps on moving like that. So here you have to put a plate. Okay, so a charged plate to deflect the particle to hit the target. That's here at the end when it achieves the highest radius, right? Now let's try to understand what happens. So we come to the working part of it. So let me go to this direction. We try to see the working, right? So you have a charged particle placed somewhere here, right? In the center here. Normally a positively charged, normally a positive charge is kept at the center. Okay. Now what happens? There is an oscillating electric field. So suddenly, as suppose this is positive, and when this is negative, what happens? This positively charged particle will get repelled, right? It attains a velocity, right? Suddenly, in what direction? In this direction, right? Now, the moment it does that, there is a force that starts acting in the upward direction. Q V cross B. This is your V. B is inside, right? So I have a V here, okay, and the B is into the plane of the paper, so plane of the screen. So it is something like that. This is V. This is B. So V cross B comes up, right? So it points up. It points up. So it points in this direction. This is the force that it feels, and due to that, it'll try to move in a circle, right? So between these 2 points, between the D's from here till here, it has gained some speed and bends like that, right? In the counterclockwise direction. Now the moment it enters this D, say I name this D2, okay? I name this D as D2, okay? So this is D2, Okay, the moment it enters D2, the electrostatic field inside the shell and inside the hollow metal conductor, that goes to zero, and there is no impact of that, right? So what happens, it comes full circle like that. Okay, it kind of stops accelerating, and with whatever velocity it has attained, it will be it will be it will be moving in a circular fashion where r is equal to mv upon qb.
The energy would be
Yes.
What will be moving in the circular fashion?
This particle, the charged particle, the positively charged particle, which was in the beginning at the center, right? So normally it is kept at the center, and hold on, and as the plates get the voltage, it accelerates, right? It accelerates, and moves in a circle. Now what happens? As it enters D2, as it enters D2, there is no electric field. There is no electric field inside the D, and it continues in a circular path of radius r such that r is equal to mv upon qb. Correct? This is what we had derived yesterday. Now what happens? It comes here. It comes here, and and we arrange our oscillator frequency such that when it comes at this point, exactly at that point, okay, exactly at this point, the potential here flips to positive, and this becomes negative. Now what happens across this d? This again accelerates, and the velocity gets increased, and an increase in velocity results in a larger r, right? Now, okay, so the oscillator frequency is kept equal to the oscillator frequency the oscillator frequency is kept equal to the cyclotron frequency. Cyclotron frequency. So you keep nu O is equal to nu C.
So how does the cyclotron have its own frequency?
Cyclotron has its own frequency in the sense that we had found out that T is equal to 2 pi r upon the velocity, and that was 2 pi m by qb. So the frequency, this was the time period of of the cyclotron. This was the time period of the cyclotron. This becomes the frequency of the cyclotron. That is 1 by T naught is equal to QB upon 2 pi m. Now that is as we had already discussed, and you can see here as well, that is absolutely independent of any R or V, right? So once you have fixed what the charge is, and what B is and what M is, this becomes absolutely fixed, and it has nothing to do with anything. So even though the radius is increasing, the frequency at which it keeps on appearing at the edge of these two D's, that is exactly the same. That's why you are able to tune your oscillator with the frequency of the cyclotron, with the frequency of the cyclotron. And this is called, this phenomena is called the resonance condition, right? This is called the resonance condition. This is called a resonance condition. Okay, and why does it hold on? Because of this. Okay, it'll never change. It's like the rate at which the frequency with which they keep on appearing here, that never changes, right? So what happens? The oscillator frequency is kept equal to the cyclotron frequency. As the cyclotron, as the particle enters the exits, or particle comes to the edge of D2, it accelerates and enters D1, and sweeps a circle of bigger radius, isn't it? Circle of bigger radius, and this keeps on happening. Okay, again it enters D1, where there is no field, electric field, and it does not accelerate. The velocity remains so constant. So it again enters here, right? Enters here. The radius has become bigger. Comes here again. The moment it comes here, this becomes positive. This becomes positive. This becomes negative. It again accelerates, gains velocity. The radius has become bigger. You see that?
Why is the radius become bigger?
Because of increased velocity between these two D's, the electrostatic field is there, and it accelerates the charged particle. Okay, if it gets accelerated, the velocity goes up. If the velocity goes up, then R goes up, right? Again it comes here. When it reaches this point, again the polarity is positive here and negative here. It gets accelerated here, velocity again goes up, it kind of goes in a larger radius. Again it reaches here, this becomes positive, this is negative, again accelerates, moves in this circle of a greater radius. Again this becomes positive. It keeps on happening, right? That keeps on happening. This becomes positive, this is negative. Why? Because I've been able to tune it to that frequency. Every time that it appears at the edge of this, the field has flipped. Okay, so if this was not true, if this was not independent of radius and hence velocity, then you would not have been able to design a cyclotron. Get that? Because things are happening so fast that and these accelerate to such great velocities, say to 1/100th of the speed of light, that or it starts nearing the speed of light, that you won't be having time physically to kind of switch the field. And if you're not able to switch the fields, at times it will accelerate, at times it will decelerate, and the whole purpose of designing the cyclotron gets defeated, right? So the particle comes to the edge, it accelerates and sweeps a circle of bigger radius. And at the exit of D1, at the exit of D1, the polarity of voltages across D1 and D2 accelerates it further, accelerates it further, accelerates it further, and it sweeps a circle of bigger radius. And that goes on. And so on, right? It keeps on going on till it attains a radius that is approximately equal to the radius of the D, right? The radius of the D. So when you start nearing somewhere here, right? As you are somewhere here, let's say this radius is R, right? We would like this particle to be deflected onto the target, to be shot at the target, right? So, so as the radius of the particle increases, as the radius of the particle increases, we deflect it away by a plate. We deflect it away by a charged plate to hit at any target. Now you understand very well. This is a positively charged particle. It is furiously moving in a circle, and you want to take it out of that circular motion. So you will have to keep a negatively charged plate somewhere here, right? So a negatively charged plate, only a huge pull by this plate will be able to attract it here and take it out of that circular trajectory that it is going on in, right? It's going on in. Fine. Now, as the radius goes up, okay, let us try to see what our as our radius approaches, as r tends to capital R. Let us try to understand what my energy of the particle will be, half into m into v square. So we have that relationship where we have r is equal to mv upon qb, right? So so mv is nothing but rqb. So for half mv square, what do? We kind of square this, m square v square, that is r square q square b square, and I divide it by m, right? Half m on both sides. So multiplying by half m, multiplying by half 1 by 2m into m square v square, it gives me r square q square b square upon 2m, right? So half mv square becomes equal to R square Q square B square upon 2m. Now you must understand why we were so bent upon increasing the radius. As the radius goes up,
Energy
Speed
that means the
increases.
velocity is going up. That means the particle is becoming more energetic, right? So as its velocity reaches our desirable velocity, we stop the process and deflect it out of the system. Okay, and
How big can a cyclotron be?
how big can a cyclotron be? That's a good question. It can be kind of be as big as a cyclotron of radius, say 5 meters or above. Okay,
why?
Speed would be
because if the radius goes up,
speed goes up.
the speed goes up.
So
More energy.
Because there is a limit to what B you'll be able to gain, right? Gaining, making B higher and higher is not always the solution.
mass को high कर देते हैं.
Also, making mass higher will reduce energy actually.
It reduced emissions.
Okay, you have to have more charge on the same mass, right? So, so that and okay, and you'd also like some time, right, before kind of it moves and hits. So it's a very small one. The moment you switch it on, it kind of goes and hits it, right? So there are so many other parameters because if you start increasing the B, then you have to cool it, as you have to do it in an MRI machine with a liquid helium or something, right? So they are electromagnets, so you'll be circulating a huge amount of current into that to create a very huge amount of field. Okay, so the things start becoming bulkier and bulkier as you start moving it ahead. So for example, in India, you have the Center for Advanced Technology at Indore. We call it CAT, Indore. Okay, this place does have a cyclotron entirely to itself. Okay, now why do you want to do this? Okay, why do we want to accelerate the particles? So there must be certain applications for this, right? The applications are that you might hit the nucleus of an atom and try to break it. Okay, so hitting the nucleus of an atom to break it and study the atomic structure. Study the atomic structure or nuclear behavior or nuclear behavior. You can implant ions into the metals, right? So implant ions into metals and study the change in their properties. The change in their properties. Also, you can bombard the nucleus of certain species and make them radioactive. Okay, so bombard the nuclei and make it radioactive or make it undergo a fission reaction, right?
This cyclotron can be used as a nuclear weapon.
Not exactly as a nuclear weapon, but let me tell you, bombard the nuclei and and make it radioactive and induce a chain reaction to treat certain forms of cancer. Okay, you can induce a chain reaction as you do in a nuclear reaction and keep on emitting radiation so that you can do some radiation therapy. Fine. But the guiding principle of this is indeed the resonance condition. So the principle of working is that the frequency of frequency of the revolution is unaffected is unaffected by the velocity of the particle. And that leads us to set new oscillator is equal to new c. This is very important.